Welcome, this is Art Emmen reporting live for Premier from the ISC conference in Frankfurt. And we are here with Christopher Snabel from IBM, who will explain us a little bit about quantum computing. So, welcome.
Yeah, thank you. We're really excited to be here so that we can share quantum computing. Online, we've already had, as IBM launched over a year ago, a real quantum computer that anybody can use at ibm.com/IBMQ. That's a 5-qubit system, and we've also launched a 16-qubit system. This is important because quantum computing, compared to classical computing, allows us to tackle certain problems that we could otherwise have no chance of being able to solve. These are problems that scale exponentially with their run times. For example, there's types of problems like the traveling salesman problem, where a salesman needs to move between different cities and try to find that optimal path between those cities. This turns out to be a very, very complex problem to solve. If I have 57 dots on a map, that's 10 to the 76, so 10 with 76 different possible ways to move between all those different cities. This is something that, as I continue to grow that set, will become harder and harder for a classical computer to solve, to the point that it's no longer possible. So with quantum, we identify different types of algorithms that can be used to be able to tackle these kinds of problems. Quantum, the way it is architected, is just fundamentally different, and it allows us to explore this exponential set of possibilities and be able to come upon that one correct solution to the problem. This is something that can be used in a hybrid way and complement what we do with classical, so you can see that almost as an accelerator, but it really needs to have that different way of interacting in different types of algorithms to take advantage of. So this is something that you can take advantage of as well. So again, I said that IBM.com, IBMQ has these systems for you to use. It's for free, and there's different types of users guides. You don't need to be a quantum physicist. You don't need to know anything about linear algebra. There's a beginner's users guide that you can step into and learn how to use the program yourself. We also have a commercial program where IBM is going to offer the most advanced quantum computing hardware to the world in a commercial program with the first systems delivering this year. We'll be at 50 qubits within a few years within our commercial program. And the reason that that's important is because at 50 qubits, you're suddenly at that point where the world's largest supercomputer is no longer able to simulate what that system can do. And that can get interesting because, well, I have something that can't be done, but then it's really a question of, is it something valuable? And that's the work that needs to be done with these systems right now, is to identify those different types of use cases where we can now take something in that 50 to 100 qubit time frame and look at how do we take advantage of the system, how do we map real problems so that we can do something useful with these systems. We believe at IBM that it's not the stage and power of the systems that's going to be the real limitation. The real limitation is going to be our own imagination and our own skills and being able to map the problems from what we've traditionally done in classical, expand that to the space that we could not before access, and figure out how to do those on these near-term quantum systems. So these systems right now, they're relatively small. They're qubits that have errors associated with them. And that's going to be this interim time frame before we move to much larger systems that are fault tolerant, that are universal. Fault tolerant meaning they don't have errors. So I need multiple, perhaps up to 1,000 physical qubits to create one logical qubit with no error. A universal quantum computer meaning I have a full set of gates that can be applied to be able to map any type of algorithm onto the system. So there's been different discoveries in the field of quantum algorithms. For instance, Shor's algorithm, which you may have heard of, because it helps factor very large numbers to their primes. This type of factorization required, for instance, to defeat encryption, would require this type of fault-tolerant universal quantum computer. So while IBM has a system that moves us towards that path, that's still decades away, and in the meantime, we have approximate universal quantum computers. So these quantum computers that still have that universal set of gates, but where I can implement algorithms that can mitigate and tolerate that error that's inherent in our system. So the real trick right now in quantum computing, and a lot of the work and research that needs to be done, is around how do I take those problems, how do I map them to those approximate universal quantum systems that I'm going to have in the near term. So, and then of course you have the opportunity then at this website to learn about that and to explore it, and we really do hope that you take advantage of that, because we're at the beginning of a very long phase of learning how to apply quantum computing, and here at IBM we're certainly very excited to be a leader in this and to be able to help move the world into this next generation of computing.
You said a qubit, 50 qubit computer is just the same size as the fastest computer in the world today. If you have a 25 qubit computer, is it half as fast, or doesn't it work that way?
Because of the notion of how these quantum computers scale, as I add qubits, it gives me an exponentially growing set of a space within which to work. All of these qubits enable superposition within the different pieces, and what that means is the maximum opportunity is each time I add a qubit, I'm doubling the amount of possible paths through the system. However, that's really the maximum. When you talk about what's the power of a quantum computer, particularly in this approximate universal quantum computing space, we need to talk about a notion of quantum volume, which is really, what type of compute am I able to do with this system? So if we look at our 5 qubit compared to our 16 qubit, the 16 qubit has about twice the quantum volume as a 5 qubit. And why is that? Well, we've grown the number of qubits, but we also need to drive error rates down. We also need to improve the connectivity within our system. Not all qubits are connected to all other qubits. So when we look at from our 16 qubit system to our 17 qubit system, there again we're going to about double the quantum volume. So quantum volume is really that measure of power that you need to use within a quantum system.
What type of power consumption does a quantum computer use? Is it more or less than a...
Well, what's really interesting about it is if you look at the processor itself, the processor is superconducting. So, I mean, the power consumption of the processor itself is very low, though the system is effectively looks like a very large refrigerator. It's a cylindrical refrigerator, and the processor is kept at 15 millikelvin. So we use commercial components to be able to refrigerate that using closed loop system pumping helium. So a lot of the power consumption is really driven by the cooling to be able to maintain the system such that we can maintain the superconducting state of the processor, as well as being able to keep the noise levels low, because again, a large part of quantum volume is being able to keep those error rates.
Thank you very much for this interview.
Well, thank you, and I hope everybody takes advantage of the IBM Quantum experience. It's there for you to use.
For Premier Live, this was Atemen reporting live from Frankfurt.